Alright, let's look at theorem 1, parallelism in absolute geometry. Right. So it says that if you have two lines, L and M, and transversal going through both of them, and then their alternate interior angles are congruent, then we can conclude that L and M are actually parallel. Alright, so let's try to prove that. Alright, so first, so we assume that the 1, so what's given is alternate interior angles are congruent. So angle 1 and angle 2 in the picture, I'm going to just use that notation. So angle 1 is congruent to angle 2. Right, so this is given. Alright, so for the sake of argument, let's assume that they're not perpendicular to parallel to each other. So L is not parallel. Oh, actually, maybe I should say assume that L is not parallel to M. Right, so this would be the assumption for indirect proof. Right, so 3. Alright, so if that's the case, there's gotta be, so L will meet M at some point, say C. Alright, so this comes from the assumption line 2. So the picture actually looks more like this. So you have a line here. So this is L. Right, but these two guys actually intersect because they are not parallel. So it's going to look like this. And then you have a transversal like that. Alright, so T. So here is the angle 1, and here is the angle 2. Alright, so we have, say this is A, and this is B. Then you have C there. Alright. Then if you pay attention to the triangle right here, triangle ABC, if you can form a triangle, we know that this number 2, angle 2 is the exterior angle, and the 1 would be the opposite interior angle. So which means that the 4, alright, measure of angle 1, or measure of angle 1 is strictly smaller because it's an opposite interior angle than the measure of the exterior angle, so angle 2. So this is exterior angle inequality. Alright, which is a contradiction because they are supposed to be congruent. Right, so therefore these two guys are parallel to each other. Right, so this is rule of elimination. We eliminated the case where L is not parallel to M. Alright, that's it. And note that the converse of this statement, it cannot be proved using without using extra axiom. So here, note. Right, the converse, is not true in absolute geometry. Right? That's it. I hope that this was clear.